So, hello, today I want to talk about a very special galaxy and why and how it's so special, everything in this video, so listen up. A distant galaxy is flaring with strange regularity and scientists have figured out why. Roughly every 114 days, almost like clockwork, a galaxy 570 million light years away lights up a firework. Since at least 2014, our observatories have recorded this strange behavior. Now astronomers have put the pieces together to figure out why that happens and everything what they found out now. In the center of the spiral galaxy named ESO 253 G003, a supermassive black hole is being orbited by a star that every 140 days swings close enough for some of its material to be slurped up, causing a brilliant flare of light across multiple wavelengths. Then it moves away, surviving to be slurped again on its next approach. Because of the regularity of the flares, astronomers have nicknamed the galaxy Old Faithful, like the geyser in the Yellowstone National Park. These are the most predictable and frequently recurring multi-wavelength flares we've seen from a galaxy's core, and they give us a unique opportunity to study this exogalactic Old Faithful in detail, said first author of the study, astronomer Anne Payne at the University of Hawaii at Manoa. We think a supermassive black hole at the galaxy center creates the burst as it partially consumes an orbiting giant star. The flares were first detected in November of 2014, picked up by the All-Sky Automated Survey of Supernovae ASAS-SN. At the time, astronomers thought that the brightening was a supernova occurring in ESO 253G003. But in 2020, when Pioneer was looking over the ASAS-SN data, the ESO 253G003, she found another flare from the same location and another and another. In total, she identified 70 flares, spaced roughly 140 days apart. She and her team predicted the galaxy would flare again on 17th of May, 7th September, and 26th of December of 2020. And they were right. They named their repeated flaring ASASSN 14KO. And those accurate predictions meant they were able to take new, more detailed observations of the May flare with NASA's powerful TESS telescope. Previous observations from other instruments also provided data across a range of wavelengths. TESS provided a very true picture of that particular flare, but because of the way the mission images the sky, it can't observe all of them, said astronomer Patrick Valley of Ohio State University. ASAS-SN collects less detail on individual outbursts but provides a longer baseline, which was crucial in the case. The two surveys complement one another, but the supernova flare just once, then fades since such an event destroys our originating star. So whatever was causing the eruptions of light in optical, ultraviolet and X-ray wavelengths had to be something else. A supermassive black hole emitting regular flare as it snacks on an orbiting star isn't unheard of. One was identified last year, one on a 9-hour flaring schedule, but the case wasn't as simple as ESO 253G003. That's because ESO 253G003 is actually two galaxies in the final stages of merging, which means there should be two supermassive black holes in its center. Recent research has shown that two interacting supermassive black holes can cause repeated flaring, but the objects in the center of ESO 253G003 are thought to be far apart to interact in this way. Another possibility raised was a star crashing through an accretion disk of material swirling around and feeding into one of the black holes. This had to be ruled out too, as the star crashed through the disk at different locations and angles. The shapes of its flares should have been different, but the observations showed that the flares from ESO 253G003 were too closely matched. The third possibility was repeated partial tidal disruption, where a larger massive object repeatedly strips material from a smaller orbiting one. If a star was on eccentric 140-day orbit around the black hole, its close approach or Reese Eastern could see it veering close enough to have material strip before it hurtles away again. When this material collides with the accretion disk, it causes a flare, and this is what seems to be happening. With this scenario in mind, the team analyzed observations. They analyzed the light curve of every flare and also compared them to other known black hole tidal disruption events. And they determined that the star was likely orbiting a supermassive black hole clocking at 78 million solar masses. At every closest approach, the star losing around 0.3% of the mass of the Sun, about 3 Jupiters, to the black hole would be sufficient to cause the observed flares while allowing the star to live on. If a giant star with a puffy envelope wanders close but not too close on a very elongated orbit, then the black hole can steal some of the outer material without ripping apart the entire star, said astronomer Benjamin Chappie of the University of Hawaii Institute for Astronomy. In that case, the giant star will just keep returning again and again until the star is exhausted. It's not clear how long the star and the black hole have been maintaining this dance, which makes it hard to calculate how long the star has left. But the team has predicted when the next two flares are due to occur in April and August of this year and have planned to take even more observations. It represents an extremely rare opportunity to understand supermassive black hole mass accretion. In general, we really want to understand the properties of these black holes and how they grow, said astronomer Chris Stanek of Ohio State University. The ability to exactly predict the timing of the next episode allows us to take data that we could not otherwise take. And we are taking such data already. The research has been presented at the 237th meeting of the American Astronomical Society. It will also be submitted to the Astrophysical Journal and is available on ARXIV. Thanks for listening. That will be everything, and goodbye.